always does something like this. So, part one of the fundamental theory of calculus, we kind of glazed over last week. Like we said, that the derivative and the prime cancel each other out. So the fundamental theorem of calculus part one says that if you have a continuous function, then capital F of x will always equal, oh wait, I forgot. And I just did a little quick thing, and then I saved the notes. People that go back and look at the notes, the box is still in. So it says the integral from a to x of little f of t. That function has a derivative at every point in the interval from a to b, and the derivative df over dx. I almost did. And just like mean value theorem, fundamental theorem of calculus, FTC is accepted abbreviation. When we get to the practice AP exams, I have worked out solutions that I've done, and I try to put stuff next to it, like why it works, and like there's multiple choice questions, and I write FTC part 1. But that's what I was doing to do that problem. So, so just like we said last week, maybe a little more theoretic here. If you take the derivative of the integral from a to x of the function, then you will just get back f of x. So we kind of proved that last week with the whole f of b minus f of a thing. Basically just saying the derivative of the integral cancels it out when you're doing that. So I think I didn't put the next slide on there. Maybe. Oh, I did put it on there. I think it's really important to read this because, like, you kind of look at it and you're like, yeah, the derivative and the integral cancel each other out. But it says everything that this little statement says that you just wrote out. It says that every continuous function is the derivative of some other function. Have you ever said that before? Every continuous function f is the derivative of some other function, namely that integral. This statement also says that every continuous function has an antiderivative. And it says that the processes of integration and differentiation are inverses of each other. If any equation deserves to be called the fundamental theorem of calculus, this equation is surely derivative. I don't think I could ever choose a calculus book that I didn't because it makes me so happy. So this is not like what we're going to do today isn't mind-blowing, but it's important, and it's important to understand what this does, and it shows up on the AP test, because I feel that we can go with this class. So today the questions say find dy dx. The derivative, but notice these are all integrals. So, right? So when you're taking the derivative of the integral, it just cancels out using that fundamental theorem of calculus. So I'm going to write out especially this first one, and then we can decide if we're going to write it. But if I want to take the derivative of the integral from 0 to x, sine squared t. One page. This says the derivative of the integral from a to x of f of t dt is just f of x. So knowing that, what do you think that this equals? Right. So let's try. This is f of t, right? So we're not doing the antiderivative. It's still still saying little f, but we're just kind of changing the t to an x. So the derivative of the integral of this is just sine squared. Multiple choice question. This always shows up as a multiple choice question on the AP test, and they always have the antiderivative in there. We'll always choose it because you see that derivative and you think that that's really they should say dy dx. Y derivative of sine. So what about number 2? What looks different on number 2 from number 1? There's 0 on number 1. Oh, the x is on the bottom. If the x is on the bottom, does that match what the fundamental table calculus says? Which means I need the x on the top. Can I make the x on the top? So I could say this is negative the integral from 6 to x of ln of 1 plus. So it's important that it has to match constant, whatever a can be any number, their x is at the top. So then when I take dy dx, what would I get? Negative ln of 1 plus x. I'll tell you, like, this question is not going to show up on it. Maybe, but more than likely, something like this would show up on the I get a little It is possible, but you got to do a little bit more work. So think about maybe like the chain rule. When we took the derivative of a function in a function, we would do the normal derivative, and then you have to take the derivative of the inside part. If this is something more than x, you have to multiply by its derivative, like by the chain. So we can still say the derivative, when I take the derivative of cosine of the integral, if the integral just equals out, that is cosine of x squared, right? Whatever this is, substitute in there. But then, since x squared is like a function in a function, I have to multiply by its derivative. So I have to multiply by 2, or 2x cosine squared. So it's like the integral part cancels out, but what you substitute in, you're still taking the derivative of that. So putting it all together, look at this one. We've switched the order, and we have an extra, it's not just x up there. So take a second or a couple minutes and try that. One-third minute. It's been like it's always that, it's at the top row of the wall. You could do a U substitution if you wanted to, like if you wanted to make this unit and then multiply by u over dx. Like I said before, I don't usually use U substitution with my derivatives very much. Oh, on a side note, do you know what Miley Cyrus song is called 7 Things That I Hate About You? I've never heard of it in my life, but last night I found a song called 7 Things I Love About You. is. I maybe listened to it like 7. It would never happen. I'm very anti-tattoo. I kind of think I'm this open-minded person, but when it comes to tattoos, like, no tattoos. My husband wanted to get a tattoo. Like, he said, oh, I'd like to get a tattoo in this part. Okay, like, what's happened? And then his friend had a tattoo party. And he was like, oh, Joe's having a tattoo party. I could go and get a tattoo. And then I, like, walked. And he was like, if you didn't want me to get one, you could have told me the first time. My husband was like, I want to do it to honor Parker or whatever. And I was like, if you want to honor Parker, like, buy a singing box for him. Like, don't waste money on a tattoo. Like, I don't know why I was saying. You're good. Hi. Really small tattoos. How much would one digit be? Alright. Negative. My derivative is 1/2 x to the negative 1/2, right? So, like, here's where calculus gets exciting. Your brain has to go with from derivatives and integrals sometimes in the same thing. That's exciting, right? But this one is just going to be negative. I'm going to write it as 1/2 radical x times sine of, right, when you put the square root of x in there and it's squared, that's just very good. I could go up there if you want to, negative sine of x over 2 radical x. Some version of that. So taking the derivative of the integral when x is up there at the top, like, that's the big key. Because if it's just a number to a number, like, you're going to get a number answer. But when there's x up there, you take the derivative of that. That's the number. So the only other thing, and your book has a really good example of this that I feel like is they kind of make you go the other way, and they say construct a function of this form. So they want you to write the integral from a to x of f of t dt plus c. Oh, maybe we've been failing. That satisfies the given conditions. Example 4 in your book. So here's a function. And they tell me that y equals 0 when x equals 8. I'll do this part. So the function part actually is pretty easy. If this is my answer, what could my function be? Oh, I go back to yeah, I just changed my x's to t's, so that's e to the t tangent of t dt. I know, right? So here's the, oh, I got this part for you too. X goes here. So then the big question is, what number goes down here, and is there some c value over here that we have to think about when we do this? So if they tell me that y equals 0 when x equals 8, that's like the ordered pair 8, 0. So Grady says 8 goes on the bottom. Does it make sense to you that the x coordinate should go down here on the integral line? When we do our integrals, like what do those numbers on the integral represent x values or y values? You're just guessing.
Guessing.
When I say I'm taking the integral from a to b, those are x values, right? And then we plug them up. But then you change your answer very quickly when I didn't confirm you that you're correct. Be confident. So those are x values. So does it make sense that 8 should go there? You called every possible answer. So then the c value is if it starts somewhere other than when y equals 0. So in this case, it would be like plus 0. Because if it started somewhere higher up, it would be have I ever seen something like number 5? I haven't. But I think it's worthwhile to think about these just to kind of help you think about where that is coming from. Example, I think it was the example 4 in your book kind of goes through that in a little more detail. Like they have one where the original condition is when x is 3, y is 5. So then they have a 5 out there. If they give you that. They don't give us this condition on the other ones, but they're asking us to solve this, so they're telling us already. Like, what if they gave us one to evaluate that said, like, 7 here, when we take the derivative of all this, what's the derivative of 7? What's the derivative of 7? 0. So that's why, like, even if there was a number out there, when we take the derivative of it, it kind of goes the same. But if you were going backwards from the derivative back to this, that's why it's looking out. Is that it? So I don't think this homework's that bad, but definitely every other one's odd. Check your answers. The first couple are great because it just has x in the top. But if you're switched, remember to pull the negative out. If there's something other than x up there, you have to put the derivative in. And then tomorrow we'll do FTC part 2, which is the whole FTC kind of essay, and we can go crazy with it.